Hi everyone, this is Lab 4 Oscillations. The purpose of Lab 4 observes the motion of a spring mass system that both stretches and swings. This motion is modeled using computational models in GlowScript. The motions from this lab are based on the physics principles, which is Newton's second law, also known as the momentum principle, which relates the net interaction between the system and its surroundings. The formulas that will be used mainly consist of spring motion and the update formulas. This lab explored the two-dimensional motion of a spring mass system that both stretches and swings. Using Tracker, I collected the x and y position data and imported it into a GlowScript Python model based on the momentum and energy principles. The simulation's predictions were compared with experimental data to evaluate accuracy. Energy plots showed how kinetic, gravitational, and spring potential energies changed over time, allowing me to verify energy conservation and analyze oscillation periods in both horizontal and vertical directions. Part 1 Tracker. The system was the mass and spring. Its surroundings is everything outside the mass spring system like gravity. I chose option 1 using the video analysis only. I set the calibration length to 0.7 meters and plotted the mass at different frames. Tracker output the positions in the x direction and y direction, and I created a spreadsheet using the x and y position of the mass. Part 2 GlowScript. I modified the starter code to fit my analysis. I updated the initial conditions based on the tracker observations, like the initial position and the initial velocity. I also used the forces spring formula to calculate spring force, and using the spreadsheet, it gave me this output, which is an image of the spring motion. Part 3 Comparing Models. For forces, the computational model includes only spring force and gravity. It assumes no air resistance or friction, while the experimental data includes real-world effects like air resistance and imperfect spring behavior. For energy, the computational model includes total energy, kinetic and potential, and it remains nearly constant, showing ideal conservation. And experimental data also includes total energy, kinetic and potential, but it gradually decreases. For trajectory, the computational model was smoother and symmetrical, while Tracker showed slight variations due to tracking and experimental imperfections. Both also used the same initial conditions. Part 4. Some possible sources of error include inaccurate calibration or scaling in Tracker, and also human error in making the position of the mass frame by frame. Part 5. For the first question, is the energy principle satisfied? The energy principle is satisfied for the model system. The plots show that while kinetic and potential energies vary out of phase, with kinetic energy is the highest when potential energy is the lowest, the total energy remains nearly constant throughout the motion. Small fluctuations in total energy are likely due to air resistance, friction, or minor experimental inaccuracies in the tracker data. For the second question, from the tracker data, the oscillation periods are estimated from both the x and y position plots and are approximately 0.08 seconds. Minor discrepancies may result from the camera angle errors or measurement uncertainty, but overall, the data supports the expected periodic behavior of the spring mass system. In conclusion, the energy principle was satisfied. The total energy remained nearly constant throughout the motion. Oscillation periods from both the x and y data were consistent, and minor differences likely came from air resistance, friction, or tracking position. Overall, the experiment supports the accuracy of the energy conservation model for the oscillating system. Thank you.